let's walk through a couple examples of how I expect students to practice and then be able to interpret chemicals. Um, and so we're not going to worry about space filling models and all of that. We just want to look at how we're interpreting or how we're building a chemical formula, since we'll be using that more than anything else. So for my examples, I want to use common solvents that are used to extract cannabis plants, to extract THC and CBD out of them. So we're going to start with butane. So here is butane's chemical formula. And I'm going to draw it for you and give you that information, but I don't expect you to do that. But let's work through the interpreting that I expect to happen. So if you just saw this chemical formula, you read it C4H10, I would start noticing and noting this information. One, that this molecule has only two elements that make it up. So it has carbon and it has hydrogen. And then I'm going to notice that the amount of carbon to the amount of hydrogen is captured in the subscripts. And so that means I have 4 carbon atoms. And I have 10 hydrogen atoms. In this molecule. I'm also going to note something else. Both carbon and hydrogen are nonmetal atoms. I don't have a metal in this chemical formula at all. And so because of that, I'm going to assume, and it might be a guess, I could be wrong, but it's very likely that this is going to be a covalent molecule and not an ionic compound. Those ionic compounds typically form between a metal and a nonmetal. So if I don't have a metal present here, I'm going to assume this is a covalent molecule. And that would really mean that we have the situation where the atoms' electron clouds are overlapping with one another. And so that's what I think is really important here. At this phase, we're just going to work up on chemical formulas, interpreting what they are and their ratio. Later, what we'll do is we'll build out and say, okay, well, these are carbons are connected to one another, and each carbon is also connected to hydrogens through something like a Lewis structure. And so we'll take these chemical formulas and interpret them that way and kind of then have an idea of their shape. So this is a later activity. Let's look at a different one. Here's ethanol. So I want us to interpret the chemical structure now into a chemical formula. So this is a picture of how the elements, the atoms of ethanol are connected to one another. So let's first kind of organize this. So I'm seeing carbons here. I'm going to list these out over here. So I see 2 carbon. You see 1, 2, 3, 4, 5, and 6 hydrogen here. And then lastly, I'm going to see if I have anything else. It looks like there's an oxygen. Oh. It looks like there's just one, so I just have 1 oxygen. Okay, so I now have kind of the ratio. I know how many of each type of element I have, and I know which elements I have. So I just have carbon, hydrogen, and oxygen. So carbon, I'm going to look at my periodic table, and I'll find the name if I need to find its chemical symbol. So carbon's chemical symbol is C. If I look up hydrogen, its chemical symbol is H, and oxygen's is O. So these are all ones where the chemical symbol is just the first letter of its name. We'll get into other ones where that's not the case, especially lower down in the periodic table when like we're kind of having to get more creative about names. It's like, for example, tungsten is spelled or its chemical symbol is a W. All of these have just one letter chemical symbols, but if you look at the periodic table, you'll see some that have multiple. So we just were looking at sodium and chlorine. And these are both chemical symbols that have two letters. And you'll note that it's important that the first letter is capitalized. And the second letter is lowercase. This is so we know in a string of letters which are elements. And so if I wrote chlorine as two capital letters, sorry. I might think that I would interpret this as saying this is carbon and something that starts with L. I actually don't know if we have one that just starts with L, honestly. Here's another one where you could be like, say this. CO, that is a an uppercase carbon with a lowercase oxygen. This is cobalt. But if they're both capitalized, this is carbon and oxygen. So we use the capitalization of the first letter to indicate that it's a new element. All right. So bit of a tangent there. Let's go back to our example of ethanol. We have carbon, oxygen, and hydrogen. We have their chemical symbols and we have the number of atoms that we have of each. So we're going to build our chemical formula. We typically start with the carbons and then follow with hydrogens and then the other elements. Sometimes the hydrogen's written first. Usually the metal is placed in the beginning too. These rules I can print out for you if you're interested, but normally we'll see these in, and our best guess is usually fantastic. The order of the chemicals doesn't give you any information necessarily about what the structure of it is, unless you're looking at something called a structural formula, which is a little bit more, it's kind of like in between a chemical formula and a Lewis dot structure. So we're going to put these symbols in order. We've got carbon, we'll put our hydrogen next and our oxygen. Then we're going to come in and use as subscripts. So in this space right here, following it, the number of each of these atoms that we have. So our carbon has 2, our hydrogen has 6, and our oxygen has 1. For the ones, we are going to omit ones in our ratios. If we are writing the oxygen atom symbol down, chemical symbol down, then we assume there's at least 1. And so if we're writing the symbol, that's 1. Any more than that, we'll put a subscript number. And so we would write ethanol's chemical formula like this, C2H6O.